This is a dyno graph for a brushless DC motor, and it's published by Milwaukee for their Milwaukee M18 tools. So as far as I know, this sort of information isn't available anywhere, so this is like an absolute goldmine of information for anyone that likes to nerd out on tools. Motor dyno graph has the efficiency, power in mechanical power, and speed as a function of the load on the motor in torque. So it gives you amazing amounts of information. And it's published by Milwaukee. I never thought something like this would ever be available. But it was found within this patent. I'll link it in the description. It's a patent from Milwaukee, and it was initially filed December 2022 and published June 13, so almost 2 months ago. I found it because it was linked by Dorsum Tools. If you're familiar with him, he does tool videos and he often publishes videos on patents by Milwaukee. But this patent about something called a Consequent pole motor, it's talking about a different configuration of motor. So here's your standard, or what they call the conventional motor with the alternating north and south poles. This is a Outrunner motor, so the center part is the stator that stays still and the outside rotates around. And it's a 10 magnet alternating between north and south, which I've coloured in. And they're talking about a modified motor where they only use half the number of magnets and they're able to achieve similar and sometimes better performance. So here's your conventional motor, 10 magnets. Here's where you just take every second magnet out and don't change anything, and that makes a worse motor. And then they talk about this Consequent pole motor, simple motor. You get a lower flux density and longer flux lines compared to this Consequent pole motor. But anyway, that's not what's interesting. What's interesting is these dyno graphs. This one here is a Outrunner motor. It's a 10 magnet 12 coil Outrunner, so similar to the ones we just saw in those pictures. So in this one, the conventional motor is quite powerful, 3,300 watts, and peak efficiency of 85%. The 5 magnet motor is close to half of that, only 1,900 watts and 70% efficiency. It's a bit hard to see the curves, but the 5 magnet motor, that's its efficiency curve, and that's its power curve, so much worse. Whereas the Consequent pole motor doesn't get the same power, but kind of matches it on efficiency. And at low levels, this dotted line here, you can see the Consequent pole motor actually has better efficiency at low loads. And this is its operating region here. It's got this little brace here. So typically this motor, it says it's a 3,300 watt motor, but in its operating range, it's actually more like a 1,900 watt motor. Fairly fast motor, 39,000 RPM. To me, this is amazing, being able to see the efficiency of the motor. We can see it's peak efficiency at 85% and peak power it's dropping down to, well, they stuffed the scale up on this, but it's probably around about 70% because it's the same height as that. 70% at peak power. I think the rest of the graphs now are all inner pole motors or an Inrunner. This one's your very sort of standard 4 magnets on the inner part and then 6 coils around the outside as the stator. And the Consequent pole motor gets relatively similar performance. Doesn't quite get the same peak power, but in the operating region it's about the same power and efficiency. So this one is a, well, they call it a 1,400 watt motor, but in the operating region it's more like 800 watts. And peak efficiency of 85%. And the Consequent pole motor's, I think, 82%. And then the 5 pole motor's garbage. It's that's its power curve. It peaks at 600 watts and peaks at 65% efficiency. Pretty high RPM, 50,000 RPM. This motor sounds like maybe an impact driver, an 800 watt motor. But yes, the efficiency is very interesting because if anyone was around for like when brushless motors first started coming into power tools, you would have heard all the marketing fluff about 30% more power and 30% more runtime, although realistically you could only have one of those, you couldn't have both. But yes, they often say that, you know, brushless motors are up to 90% efficient, but by the looks of this, nothing really ever goes over 85% efficiency. And that's efficiency of their motor. That doesn't factor in, once you go through gearboxes and whatnot, any sort of gear reductions. You can imagine this thing here is definitely getting some gear reductions. And also, I think power loss through the wires, because I'm pretty sure for their efficiency, they're measuring it very close to the motor, not factoring in power loss through the wires, which we'll see in a later graph. Well, this graph actually. So this one, also an Inrunner, 6 coil 4 magnet Inrunner, and in the text they talk about that the conventional motor has 55 grams of magnets, whereas the Consequent pole motor gets rid of 2 of those magnets and replaces it with metal, and consequently is 28% less mass in the rotor. It's hard to see, but the Consequent pole motor pretty much has an identical efficiency curve, and its power curve drops off a little bit quicker, but within the operating range it's basically identical. And then what's really interesting about this graph is they give us this extra line here for current. And I took a few little operating points. I took an operating point and got the power, efficiency and current. Mechanical power divided by efficiency will give you the electrical power. And the electrical power divided by the current will give you the voltage. So from this we can see that it's a 18 volt motor. And then I took several more points and you can see the voltage dropping as the current goes up. They've tested this motor to obscene amounts of current, like they take it up to 540 amps, and at that point it's like 20% efficient. So it's just generating obscene amounts of heat at that. So 20% efficiency, and it's 600 and something mechanical power. So 4 times that. It's like generating 2.4 kilowatts of heat and 600 watts of actual work done. So pretty crazy motor. But this is the blue region, is its operating region. So its realistic peak power is like 1500 watts, and peak current is around about 100 amps for its operating region, but they take it much further. I'm assuming that they're liquid cooling it to be able to push it this hard. This is insane. And it's still holding up relatively well at peak power, something like 70% efficiency. 60 amps is about halfway up its operating region, and it's dropped down to 18.6 volts. Then at 90 amps, 17.7 volts, 310 amps, it's at 12 volts, so realistically it would have cut off by then because the battery is going to hit a cutoff. And then at 420 amps, 9.9 volts, 480 amps, 8.98 volts. And then I did a little bit of a resistance calculation to try and figure out. I'm assuming they're using a big battery pack for this rather than a power supply, but it could be a power supply. I'm unfamiliar with 500 amp power supplies, but I think it's more likely they're just using a giant battery bank. If anyone works at Milwaukee and wants to tell us if they've seen a giant battery in a lab somewhere, let me know. So 4,400 RPM to 3,300. So maybe, don't know, maybe a large circular saw. 4,000 RPM's probably too slow for an angle grinder. Maybe a 9-inch angle grinder, not sure. But it sounds more like maybe a large circular saw or mitre saw. What's this graph? So 4 magnet, 6 coil Inrunner. Again, they're comparing conventional to their Consequent pole motor. This one's a heavier motor with 79 grams of magnets. The last one was 55. And the Consequent pole motor gives you a rotor that's 36% lighter. So this one's got a very narrow operating region. So it's designed to run at that RPM. They even say so, that it's designed to run at 42,000 RPM. This kind of tool is most likely a vacuum or blower. They're the kind of tools that tend to run at one sort of set operating point. When we do the calculations, we actually get about 36 volts. So This is going to be one of their dual battery tools. I'm guessing the dual battery blower or dual battery vacuum. At its operating point, it's 816 watts, 28 amps, and about 82% efficiency. The current is quite non-linear in this one. This one here, relatively linear, because that's what a current versus torque should be linear. Mostly linear. Obviously, as things heat up, it gets worse, but this one goes very non-linear. But yeah, 42,000 RPM, quite high for a vacuum or fan, or blower, sorry. I don't know if they're doing any gearing down or if that's just how fast they're running it. Now, last one. 4-magnet 6-coil Inrunner. And in this one, the text, they talked about the Consequent pole motor has the same efficiency. So these are the efficiency graphs. They're pretty much identical, efficiency curve. But the Consequent pole motor actually gets 5% more power. In this one, I've drawn the red one over the Consequent pole motor power because the Consequent pole motor had reasonably better power than the other one. In most of the other ones, the conventional motor was more powerful. But this one, from the calculations, is 18 volt, although with quite a big voltage sag here, down to 13.6 volts, 250 amps, nothing wrong with that. Yeah, 86%, 1000 watts, and 60 amps, 2375, 70% efficiency, and 250 amps. So I'm pretty sure Milwaukee is not going to let you drive this motor that hard. Here's our other one. 310 amps, 12.6 volts. Yeah, they might be using the same battery pack for that. Efficiency is not quite as high as I thought. I thought they might be getting peak efficiencies. This one's the most efficient, 86%. Most of the other ones are 82 to 85. So that's an 86 as well. So yeah, most of them sort of 82 to 86% efficient.